Hi, Dev. Hi, Abdullah. Thank you for joining to our weekly machine learning study jam. And today we're going to have a little bit of theory, and then we will practice the learned theory. And we continue with the machine learning crash course. And today we're going to cover the regularization topic. Can you see the screen? So we are now here in the middle of the this machine learning crash course. Let me share the link with you. This one. And we will start today with the playground exercise. So without knowing anything about regularization, but having the knowledge from previous study jams, let's just practice and see what we get from the training. And we covered the topic of feature crosses when we multiply different features to obtain linear classification of different groups. And the task one for this playground is to run the model as it is. So it is now set up, and we need to run just by clicking this play button. And with all the given cross product features. So it means this features section contains all the product features, and we don't need to change them for now. And while we run this, let's see how the output changes, and then let's do it together in case you have a different interface. I'll start, so I don't change anything and just run this. Okay, so we see here that the epochs are counting and our test loss is changing. Not dramatically, but as more epochs count, we have more steady test loss value. And we also have the training loss. And now suddenly we have this kind of strange classification. So let's see next what we're going to do next. And then we should try to remove various cross-product features to improve the performance. And why would removing features improve performance? So this is the question for you, just to analyze, to think about what's happening. So we have here some strange classification. So we have no data points here, but somehow we have blue color sometimes, and it's not the accurate representation. Let's try to remove one of these cross products, and we start the training again, and we see that, okay, let's wait a little bit more. Not bad. We don't have this strange blue area here, although it's not that accurate. Maybe let's see. Oh, okay, so as we wait for more, let's stop here. We still have here some strange color, and we don't have any data points here. Let's remove one more and run the test again. Okay, so here it's more or less dividing it on just one line on the orange and blue data set. Let's stop here, and I'll remove one more. Let's see. Okay, so, and I hope you notice the test loss value, it's decreased, right? Okay, so when we visualize these differences between testing, training data, including X and 2 dataset points and test crosses or feature crosses, we saw how the classification changes. And you can see the answers to the first and second exercise on your own. I will just emphasize that when we use the like after 100 iterations or 1,000 iterations, we saw that we have this strange blue area. And when we remove these test crosses, at least one or two, we remove this blue area. So what does it mean? Let's see the lecture, the instructor. So the topic is regularization for simplicity.
Hello, I'm Maya Gupta. I'm a machine learning researcher here at Google. And I'm excited today to talk about the second key ingredient to making machine learning work great. You guys have already talked about minimizing training loss, that is getting the examples right. And what we're going to talk about today is regularization, which to sum it up is not trusting your examples too much. As we can see in this curve called overfitting, as we go through more and more training iterations, our training loss is getting down. It's getting further and further down, and it keeps decreasing because that's what we're doing. We're minimizing the training loss. So no surprise that the blue curve keeps going down. Eventually, they'll sort of converge there. But the red line actually starts to go up. And the red line is what we really care about. We want to generalize. Even though we're training on the training examples, we want to generalize to new examples, the test examples, and we want to have low loss on them. So how do we keep the red line from going up, and what's going on here? Well, first of all, what's going on is overfitting. We're doing such a good job on the blue examples that we're starting to sort of fit to the unique perturbations and specializations of the blue examples. As an analogy, say you were trying to learn English and the only person that there was to teach you English was a teenager. At first, that would really help you learn English and you do a great job learning English. But if all you did was listen and talk to that one teenager, pretty soon you'd start to learn that teenager's slang and the particularities of their language and accent. And at some point, it'd make it even harder for you to speak English with the general population. So what can we do about overfitting? Well, regularization is what we do to avoid overfitting. And there are a lot of different regularization strategies. One is just to do early stopping, which says just stop the training before you've really converged on the training data, trying to get to where the bottom of the red curve is. But this can be a little difficult to do in practice, but often used. Other regularization strategies include trying to penalize the model complexity. And that's what we'll be talking about the rest of this section. And what we can do is we can penalize the model complexity while we're training. So far, the training has just focused on the important thing of getting the training examples right, minimizing the empirical risk minimization. Now what we're going to do is we're going to add a second term to penalize the model complexity. This is sometimes referred to as structural risk minimization. And so we're going to balance these two key ingredients, getting the training data right, but not trusting the training data too much that it makes our model too complicated. So how do we define model complexity? Well, there are a lot of things we could do. One popular strategy is to try to prefer smaller weights. That is, make the parameters as small as we can get away with while still getting the training examples right. And we could encode that mathematically in a few different ways. Today, we're going to focus on L2 regularization, also known as ridge regularization. In this regularization strategy, we penalize the sum of the squared values of the weights. And if you're familiar with Bayesian priors, this sort of says that a priori, before we've seen our training examples, we would have guessed that our weights should be sort of centered around 0 and not too big, normally distributed. So when we use L2 regularization, it does pay attention to the training data, but it tries to make sure that we don't end up with any weights that are sort of bigger than they need to be. So let's put that together mathematically again. So now our training optimization has two terms. The first term, our training loss. We want to get the examples right. And you'll see that L term, the loss term, depends on the training data. But now we've added the second term for model complexity. And here we're using the L2 regularization, which is the sum of the squared weights. And you'll notice that that second term doesn't depend on the data. It just says, hey, I want a simple model. And you'll see these two terms are balanced by a lambda. That's a coefficient that says, how much do we care about getting the examples right versus making the model simple? And the choice of lambda is really up to you and depends on your problem. If you have lots and lots of training data and your training data and your test data look the same, IID to be statistical, then you probably don't need much regularization, maybe 1 e to the -6, maybe none at all. But if you don't have much training data, or if your training data and test data are kind of different, then you may want a lot of regularization. And you may want to tune that with cross-validation or with a separate test set.
Okay, so here, just summarize what we heard. We will try to today to implement L2 regularization, and why we need this is to create a general model that will be applicable to different test data, instead of creating a very nice model that is working for one data set but is not that good for another data set. And one application for this would be, for example, you find some algorithm on internet and you want to implement for your data, and you know that your data is a little bit different from the data that was used to train the model. Maybe this is the way for you to try change the model itself by maybe introducing the L2 regularization and then test your data. As usual, there are some text. There is some text to understand in more details how do we calculate it and what's the difference between regularization with other methods. And this is also about the lambda that the instructor introduced in the end of the video. Some assumptions that we should take care of when we use L2 regularization. And when we did the playground exercise, you notice that if I waited for a sufficiently long time, we will get this strange classification onto orange and blue groups. But if I stop training at the particular point, then we don't have this overfitting of the data. So we don't have this strange blue line. So one way to decrease overfitting is to just stop training at some point before it goes overfitting, right? But we are interested in more a different way using the L2 method. Okay, so we have here, let's wait. Yes, okay. And here is the task again. We have here the, we should run the model for 500 epochs, okay? And then we need to, as usual, pay attention to the test loss on this section. And then the difference between the test loss and training loss, okay? And also we need to look at the weight. So here is features, and this is the regularization that we're gonna do today. And the rate, we can change the rate of the training, right? Regularization. So let's try the task first and see the result. While we're waiting, let's see the task 2. And they ask us to do in separate tab. We need to increase the regularization rate from 0 to 0.3, and then run the model for at least 500 epochs. Okay, so let's stop here. Oh, okay, we see here that it's a weird classification, right? Onto different groups, like 3 groups. And the difference, so the test loss is equal to 0.2 and training loss is equal to 0.1. And the difference is about 0.1, right? Let me try on the same tab. And let's run it again. And we should pay attention how the test loss and training loss differ from the first task, and what's the delta difference between the test loss and training loss and between the first and second task, and how the difference between the weight will change the outcome. Interesting. Okay, let's stop here. So we see here the classification was done better than for the first test, right? And the test loss is equal to 0.113 and the training loss equal to 0.17. So the difference is about 0.04. So it's less than for the first test we did, right? And the task 3 is to experiment with regularization rate and trying to find the optimal value. So this you can try on your own. And what we can conclude from this is that when we didn't use regularization, we had not so good trained model. I mean, the test data, the test loss, the test data was classified wrongly, right? We had 3 groups, and actually on this part we didn't have much data, but somehow the models thought that this particular range contains some orange data sets. But when we use the regularization, L2 regularization, and we use the rate of 0.3, we obtained a general model that works for this test data. And the difference between the test loss and training loss was less, right, than when we didn't use any regularization. So here is the check the understanding. Let's just try some of these questions and then move to the practice. So imagine we have a linear model with 100 input features. 10 are highly informative and 90 are non-informative. Assume that all features have values between -1 and 1, and which of the following statements are true? You can read these statements here. So the first statement, L2 regularization will encourage many of the non-informative weights to be nearly, but not exactly 0. L2 regularization may cause the model to learn a moderate weight for some non-informative features. And L2 regularization will encourage most of the non-informative weights to be exactly 0. What do you think? Any ideas? Let's try first, for example, right? So this is the correct answer. L2 regularization encourages weights to be near 0, but not exactly 0. As I understand this, so when we use L2 regularization, we want to obtain the model that works for different data sets. It means it will pick up some of the highly informative features and use no or almost none of the non-informative features. But let's say the next answer, the regularization may cause the model to learn a moderate weight for some non-informative features. Why it's not equal to 0? Because we still want to pick up some features that are maybe not informative for this test data set, but might be useful for another data set. So we're trying to create a model that will be more general than specific. And this is the wrong answer. L2 regularization will encourage most of the non-informative weights to be exactly 0. That's not true, because this L2 regularization does not tend to force weights to exactly 0. It just penalizes larger weights more than smaller weights. And as a weight gets closer to 0, L2 pushes less forcefully towards 0. Okay, and I think I will stop with the
Wait. Can I ask?
sure.
I'm not quite understand. So the L2 regularization will penalize what nodes with high loss.
So
So it will change the weight of the nodes based on what? How to the regularization define the non-informative and informative nodes.
so you ask, may I just clarify? You ask how it identifies the highly informative and non-informative features?
Yes, yes.
It's a really nice question. Let me think a little bit. So for example, let's see the example that we did before when we used computer vision for feature extraction, and we could obtain the more prominent, for example, horizontal lines that are the prominent features, right? That defines this picture, for example. And the background was blur, which is non-informative features. And L2 will put the weight on the most prominent features, and non-prominent features will force to be almost equal to 0, that it doesn't have the weight on the training data or the test data. Let me show you this formula. So here is the definition of the weight. And for example, we have here different weights with the 5 maximum, right? And if we take the squared, it's still going to be the third weight that is most, how to say, significant. So these other weights are not significant, right? So if I understand this correctly, then this weight will contribute more to the model definition or the training data comparative to the other weights.
So feature with higher weight will be more higher, like will affect more the models.
Yes. When we squared the weight, we still see it's already seen here, I think, that the third weight has more like higher value. Oh, sorry.
So it reinforces features with higher weights and penalize feature with lower weights.
Yes, but not significantly, because it won't push it towards the 0 as it would with the higher weight.
Okay.
Let's see the practice, and let me also share this code. Actually, this code was taken from one tutorial, and I'm going to set up the GitHub page and then share it with you. But for now, I'll try to send it in the chat just to quickly. I'm not sure how to send it. Okay. You can go to Google Colab, just create new document, and we're gonna use this telco, telephone, some tele company, the data from this Kaggle notebook. And let me just share this data set. So what you need to do is you need to download the data here using this download button. And then when you open the Google Colab, you need to go to the folders, and then here should be like sample data, and you need to upload this data set into the sample data folder, and try to, you can leave it as it is, but I recommend you to rename like this, rename file to telco underscore churn, because, or another name, and just pay attention that you need to change the name here when you want to read the file, CSV file. And let's see the code now. If you're ready, I'll move on, but if you need some time, I'll wait a little bit. Okay, 1 minute. Sure. Okay, if you're ready, let me start. If you have any problems with dataset or you don't know how to upload it, let me know. It would be great if we just go along together with this code. Abdullah, have you finished downloading and uploading into the Google Colab? Is there any problems? Okay. Okay. Let's first import some libraries that we're gonna use. We already familiar with pandas, and we're gonna import it this way, import pandas as PD. And then we should import some libraries from the sklearn and libraries modules and submodules. So what I want to also share with you is how to understand some code that you might not know for now. For example, we already know from Python fundamentals that we can import submodules using dot notation. For example, this is the module of the sklearn and this is the submodule, right? But I don't know what does it mean. Then I can just Google sklearn and see what train test split is. And I already, so this is actually the tutorial that we are using. And I'm going to set up the GitHub page from them and credit them later on. Just I wanted to share what the GitHub page I'm using. And this is the sklearn documentation. Let's see, wait a little bit. Just read it, the first like several lines to see the description of the module. So it splits arrays or matrices into random train and test subsets. So we can understand that why we need this library is to split our telephone company or something into test and train data. And then there is a standard scaler from the same module, sklearn, but pre-processing submodule. And let's see what does it mean. Oh, a little bit difficult to navigate through Zoom because it's always opens this toolbar. Okay, let's open. This standardizes features by removing the mean and scaling to union variance. And this is the formula how it calculates the score. This is the mu, the mean of training samples. And this is the our data set sample. And S is the number, I think. This is the standard deviation of the training samples. And why we need this, they explain here that it's better to remove or standardize the data set, especially when we want to use the L2 regularizes or linear models. Okay, now we will use the pandas library to read CSV file using .read CSV, and we should provide, if you provide just a name, I think it would maybe a mistake. So because it's a little bit difficult to navigate where the folder is. And what you can do is you can copy path and just copy, paste it here, okay? Just go to your file, copy path, and then go to the argument place. Now we will, so we define this data set as DF and like a data frame, and data frame dot fill NA. This is the method to replace the values of your data frame given some parameters. And as also when I see this method that I don't know, for example, what you should do is just read documentation. This is my advice for you. And what I see here is first description. So fill not given or non-values using the specified method. And here is the description of all the parameters that it can take. And in our case, we have the value parameter, which uses this value to fill the empty cells in your data frame. And we also have the in place. So if true, it will fill in place. Otherwise, this is default value equal to default false. So we have here 0 in place true. So it means every empty cell that we have is going to be now equal to 0. And then let me just copy this code. Is it possible? Okay. Okay. I want to run it one by one. Oh, strange. Okay, let's copy it again, and then I will paste it here. And we stopped at score. Okay, let's run this small snippet of code. Oops. Small snippet of code just to see our data, okay? Okay, this is our data, a small snippet. And we have here some customer ID number, gender, senior citizen, other different columns. And we just need to inspect them and see what are the data types for each column. For example, this is the string, this is the integer, partner is also string, yes or no. So it means, okay, there is only like two categories. They have partners or they don't. If they have dependents, children, tenure, phone service, usually we see here, for example, tenure is integers, could be different integers. But if you have this phone service, it's also the category yes or no. Same for online security and so on. We have monthly charges, which is a double. or the floats. Okay, so we inspected our data. This is the first thing that we need to do. And then we should import NumPy as NP. This is going to be used for the next line of code. So here we navigate to the churn column, and then using the dot where, we're gonna transform a little bit this column. How we transform? We write the rules in this parameter, and we see here that if the column of the churn has the values yes, then we will put 1. Otherwise, we will put 0. And again, if I don't know where, so this is what we already covered, I just need to go to the documentation and then read the example or the description. Then if I don't understand, I can see the examples. It returns elements chosen from X or Y depending on the condition. And here are some examples. It's not necessary. So I already explained here that it will take the values yes or no and put 0 or 1 respectively. So here is the category. Then we define the function. The function is convert categories, and it will receive category list, and then it has the for loop for the column in this category list. We will take this column and then define as type category. And again, if we don't know what does it mean, we should Google it. And I will just briefly explain that the data frame can have the data type category, and we convert it using this S-type function or method. And then why we do this? Because we have here some columns that are categories, right? And we need to convert them to 0 or 1 or other numbers, for example, to ease the work with these columns. And we will convert, we will rename our columns adding some string. So it's going to be underscore cat, and then it will use the dot codes method to convert it to the numeric values. And this, as we know, method, which is defined here, will not be active unless we call it. And first we need to define our category list. So we define the list, gender, partner, dependents, phone service. This is actually the names of our columns. And we parse this category list to the call of the function convert categories. So after that, we should see a different table. Let's see how it will change. Again, I want to copy it, but a little bit difficult. Let's start from bottom. Copy and then paste. Okay, let's run it. Okay, we see here why same. Oh, not same. Okay. So we have here the data frame has changed, and some values like gender, it didn't change somehow, but other categories were changed to 0 to floats. Let me just confirm. Okay. Yeah, I think it's so here we just converted to the floats, right? So we have here 0.0, 2.0. Before we didn't have such values. Okay, but the type is category. It's either 0 or 1 or 0, 2. Sometimes it's 2, 3. Okay. Then we take the total charges column. Let's find total charges column. I hope I can find it. This one, total charges column, the before last column there. And then we use two numeric method, and we will convert it to the numeric value. Why? I don't understand for now, but let's see. Then we take the same total charges and fill it with 0 if it's empty. Then we define our columns, which is this list of different column names, and define our X value, which is the independent variable as data frame columns that we defined before. So this is going to be our features that we're going to parse, right? The values that we're going to parse. Let me run this. Again, a little bit later. Okay, we see here we have gender category, partner category. So this is what we defined. And now here the gender, okay, I see. We didn't see here the 0 and 1s because we just printed the data frame that we used before, right? Because after this function, we actually should have this underscore cat suffix. And this is the columns that we use. And the values here are now of type category 0 and 1, and not just 0, 1 as integers, but as floats, because we converted them using these codes as type float. Yeah. So this is correct. And okay, we now defined our X, which is our independent variables. Let's see next. So we have here data frame churn, and this is going to be as type integer. Let's see if it was integer before. Okay, so because it was a category data, we already, I think maybe not. We didn't include it here, so we need to convert it to the category 0 and 1, and we define our Y value as the data frame churn column, because this is what we want to predict. So using these features, we want to predict this column. And then we define our training data set, the X values, the features, the Y, the predicted value from the training data set. Then we define the X, which is going to be our test data, and the Y test, the predicted Y value from the test data. And then we use the train test split, which we already discussed before. And we defined X and Y as our test or train data, test size 0.3 and random state 42. This is some parameters that we need to parse to split the data. Okay, and then we will try to define our model. And I have here prepared two definitions of the model. Why? Because we first will try to define model without L2 regularization, and then we will consider, we will evaluate what is the accuracy of the model, simple model, without regularization and with the regularization, okay? So for both of these methods, we need to import the TensorFlow layers, neural layers as dense and sequential, both of them. We already encountered them before. And also we need to import sklearn metrics, the accuracy score. Without even Googling, we can understand that this is the module to calculate the metrics the accuracy of our model. We define first the model as sequential, and then we add our layers. And as before, we define the dense layers, and the first layers are usually of the shape of our data that we parse. Then we have some other layers as activation, ReLU, and sigmoid activation. We already encountered them when we tackled the problem of computer vision, some basic computer vision problems. Then we need to compile our data. We use the optimizer atom, loss binary cross entropy, and the metrics accuracy. And I hope we will consider different types of activation optimizers later on. For now, I think it's enough information. And then we fit our model with the X train and Y train and with epochs 20. So this is we know how to do. Then after we trained our model, we use this trained model to predict Y values using the dot predict value, and we parse the test data. And then we find from this predicted Y values, we find that which is more than 0.5. And if it's more than 0.5, we substitute it with 1, otherwise with 0. And then we print the accuracy score of Y predict and Y test. So I hope it's clear. Let's run this model. If you have any questions while it's running, I'll try to answer as far as I know. Oh, it's finished. Okay, so we see here 20 epochs and the values of loss and the accuracy. And the loss is decreasing slowly to from 0.6 to 0.65 to 0.48, and the accuracy is increasing to 0.78, and the total accuracy that we have is 0.81, or yes, 81. Now the same method, so this is actually what we already run. It's not, oh no. Yes, so this is, we don't need this because it's the same as we ran before. Okay. Now we will import one more module, which is TensorFlow Keras regularizers. And this will allow us to add regularization to our model. We define model as before, sequential, add the first layer dense equal to the shape of our input data. And then on this line, what we need to add is the kernel regularizer 12. And for now, we don't need to know the details. We just know that we need to add here on the first layer. And then other layers are the same. And we fit model predict as usual, as we did before. So let's run this again. Okay, so we have a high loss, and then it decreases 0.448, almost same. Okay, so we have here 0.80. Actually, it's interesting. Before I run this on my own, it was higher, but now it's lower. Maybe because it's not good to run it several times, because I know. What a mistake I have made is we already have defined training data and test data, and it's just already trained, right? We already have all information, so it won't help us. it won't improve the training. Because of this, I need to start from the beginning. I should maybe definition of our data set is not necessary, but the line that trains and splits the data to the training data and test data should be included for sure, because otherwise we're just running our second model on the same data set, which is already trained, and it doesn't help. Let's just add it all together. Okay. Okay, let's run it again. I think the most important thing is this one, I think. Same, still same. Interesting. Okay, if you would believe me, so before I just started this study jam, I ran these codes on my own, and it was like, oh, it's even smaller. Yeah, so it was like 0.04. So it was slightly increased the accuracy, but now it's a little bit difficult to run. If you're running on your own computer, what was your accuracy points? Could you share with me? And also, this one was like 0.80, and now it's 0.81, because I think I already ran this before, so maybe it's not a good thing to run it several times. But I think this step to split the data must work, I think. Okay, so we have here accuracies lower. Dua, if you're following, could you please share what was your values of accuracy? Oh, it's higher. Oh, I should have maybe used the same values, 0.4. Yeah, so it's higher. Okay, so if I use regularization, I have more accurate test results. Maybe change the rate. Yeah. Yeah, I think in this particular case, I think the problem is that I already ran these algorithms on the data, so I just increase the test size. So I changed the data set. So when I changed the data set, I have without the regularization 0.65, and then with regularization 0.8. So we have here significantly increased accuracy when we use the regularization. But we also can change the regularizer's weight, and I need to check whether it's defined in this name, or I think that all the parameters. This is L2 regularizes, and it has 0.01. What was the accuracy for you? If you didn't, it's okay. Just curious. Okay, let's see. Oh, you didn't run, okay. Square of x. Then spider. Because you need to install it, yeah? If you use, do you use virtual environment? I use Anaconda virtual environment, and I need first to activate virtual environment. And then if you're when you activated your virtual environment, then here you need to just type with exclamation mark and then conda install TensorFlow, because here TensorFlow is already present. Conda is not found because I haven't activated Conda. I need to like source and then Conda create virtual environment, and then we can write Conda install. Anaconda, yeah. So I recommend to do this. Without TensorFlow installed, you cannot run this program. Why didn't you try to run on Google Colab? It's easy, I think, because you don't have to install TensorFlow, and it uses, oh no, it's disk, right? It's free when you use small data sets, I think. Okay, so this is actually it for today. So I think I solved the problem when I just decreased the train data. So I changed the proportion of the test and train data, which means I just changed the data that I'm training and testing, because I already ran this program before. And if I run this program over and over again, I might see even accuracy of 1.0. So it means it was already pre-trained on the same data. So we see here that after using regularization, L2, we increased the accuracy from 0.6 to 0.8. So this is what I have to explain today. And I hope to see you next week. Okay, bye-bye.